Hello, everyone, and welcome to today's desktop seminar from the Royal Society of Chemistry. My name is Hannah Fowler, and I am the Deputy Editor for the RSC's Organic Journals. This webinar series showcases leading research in topics across the chemical sciences. Today, we will continue the RSC's year-long celebration of 200 years since Michael Faraday's discovery of benzene in 1825, as two excellent speakers discuss their recent work on aromatic systems. We have Professor Renana Gershoni-Paran and Professor Dean Tantillo joining us live. This webinar is scheduled for 1 hour. Each presenter will give a talk followed by an interactive question and answer session. At any time throughout the webinar, please submit questions using the Q&A function in Zoom, and they will be asked after the presentations. But first, we just need to do some housekeeping. We must note that this webinar will be recorded, and the recording will be made available afterwards. Because of this, you will be muted, and I will relay questions during the Q&A sessions. Of course, we want everyone to be able to enjoy and contribute towards this webinar. So we'd ask all participants to be respectful of one another and to follow the agreement shown on this slide. And I'll just give everyone a few seconds just to read that. Okay, so before we start, I'd just like to take a moment to highlight that the RSC has a variety of journals relating to the aromaticity and aromatic compounds like you'll see in today's webinar. Specifically, I want to shout out Organic and Biomolecular Chemistry as our home for research on organic synthesis, methods and catalysis, as well as physical and theoretical organic chemistry. We are also delighted to announce an open call for a themed collection called Celebrating 200 Years of Benzene, which is guest edited by Ben Feringa and Nazario Martin. This collection involves a number of RSC journals and aims to take a broad perspective on carbon-based systems for both fundamental and applied research that can be regarded as benzene's direct heirs. You can find out more about the scope of the collection on our webpage. There's a short link at the bottom, and we hope you will consider contributing. So, without further ado, I'd like to introduce our first speaker, Professor Renana Gershoni-Paran. She is an assistant professor of computational chemistry at the Technion Israel Institute of Technology. She works on fundamental molecular concepts using a combination of computational chemistry, data analysis, and machine and deep learning. And she has been featured in themed collections in both PhysChem ChemPhys and Chemical Science, and had this cover article on benzoheterocyclic annihilation in ChemSci earlier this year. Today, she'll be telling us about old ideas, new tricks, additivity in polycyclic aromatic systems. So I'll now hand over to you, Professor Gershoni-Paran.
Thank you so much, Hannah, for that very kind introduction. I'll share my screen and we'll hope that this all goes smoothly. I hope that you can hear me and that you can see my screen well. So as Hannah said, what I'll be talking about are old ideas and new tricks, because benzene is one of the oldest ideas that we have right now in organic chemistry. As Hannah said, we're celebrating 200 years of it, so I thought it was a fitting topic to talk a little bit about benzene, combining with another type of very old concept in chemistry, which is additivity. So just to give you kind of a broad concept of what we're doing in my group, we are a computational physical organic chemistry group. We're interested in anything that has to do with polycyclic aromatic systems, starting from their structure and their properties all the way to their reactivity. And the work in my group generally can be divided into three main pillars: fundamental investigations of aromatic compounds, machine learning and deep learning analysis of these molecules, including generation of large databases in order to do data-driven investigations. And finally, mechanistic investigations, which we do in close collaboration with experimental groups, where we look at both how the polycyclic aromatic system might behave on its own or as a ligand for organometallic catalysts. So the work I'm going to be talking about today is very fundamental in the sense that it is an investigation of aromatic compounds and their inherent properties. But as you'll see towards the end, we actually incorporate some of our newer competences that come from the area of data-driven investigations, specifically deep learning models. So as I said, this talk combines two very old concepts, aromaticity and additivity. So what exactly is additivity? Additivity is the idea that you can take any structure, and it doesn't matter how beautiful, how complicated, how big it is, you can break it down into smaller components. And if each of those components has a specific, separate, and additive contribution to the overall properties of the larger system, then you can predict the properties of the entire system without actually having to measure it on its own, simply by taking those different contributions. Another way to say this in a more concise way is just to say that the whole is the sum of its parts. And this seems very obvious and very trivial, and in fact, it's something that we use every day in our lives as chemists. One of the most basic examples is if you think about different atomic properties, for example, the molecular weight of a molecule. If I asked you what is the molecular weight of this molecule, which happens to be caffeine, what you would do is you would add up the weights of the different carbons in it, of the nitrogens, the oxygens, and the hydrogens, and you would be able to tell me that the molecular weight of caffeine is 194.19 grams per mole. In fact, you don't even need to know the molecular structure of caffeine. It's enough to know its chemical formula because the weights of the atoms don't change depending on how you connect them to one another. And that is what is inherent in additivity. The idea that each of the components, in this case, the atoms, have a specific contribution that doesn't depend on what else is in the molecule and how they are connected to one another. We see that also in other kinds of properties. For example, we can predict the change in enthalpy for this reaction by understanding that what we're doing in this reaction is we're breaking a hydrogen-hydrogen bond and a chlorine-chlorine bond. We're making two new hydrogen-chlorine bonds, and we know the bond dissociation energies for each of these bonds. They've been measured in the gas phase. And so we can predict the overall change in enthalpy even without having to run the reaction and measure it directly. Another example of additivity is something that organic chemists use every day in the lab. If you've ever considered predicting thermochemical properties of different organic compounds using Benzone's group increment theory, you can, for example, predict the heat of formation of different molecules based on the groups that make up that compound. And so we differentiate between different types of carbons, whether in a double bond or a single bond, or how many other carbons they're connected to. And we use those different tables, and that allows us to get a prediction of the thermochemical properties of molecules, again, without having to directly measure them or even calculate them ourselves. We can also use this in spectroscopic examples. For example, we can predict the chemical shift of different molecules using these tables, just looking at where different substituents are placed on the molecule relative to one another. And this is also true for absorption spectra. UV-Vis absorption spectra. So all in all, what you can see is that additivity is a very, very powerful tool. And it's one that we use on a daily basis, oftentimes without even thinking about doing it, because it is so ingrained in how we think about chemistry. The question then becomes, are all properties additive? And obviously the answer is no, otherwise I wouldn't be asking it. So what's an example of something that's not additive? And how do we know when something is not additive? Well, we even have names for those kinds of cases. You might have heard before allosteric, cooperative, synergistic, or emergent. These are all fancy names for saying that in this case, the whole is more than the sum of its parts. And one of the examples of this is the binding of oxygen to hemoglobin. Hemoglobin is a tetramer. It's made up of 4 identical monomers that bind oxygen molecules. But it turns out that even though the monomers themselves are identical, the rate of bonding or the affinity of the binding to oxygen changes. So the first monomer binds at one affinity, the next one binds a bit stronger, the third one even more strongly, and the fourth one is the strongest. And that's not something that you would be able to predict based on the properties of each of the monomers on its own. So this would be an emergent property. So when I started thinking about properties that were interesting to me or things that I'm working on in my group, which are related to polycyclic aromatic systems, the question that came up for me was, is the aromaticity of polycyclic aromatic systems additive? Because as I said, this is the kinds of molecules that we're really interested in, and aromaticity is one of their fundamental properties, which relates to almost every other physical property that you might be interested in, including their HOMO-LUMO gap, their ionization potential, etc. And so we were wondering if we could kind of apply this idea of additivity for these molecules. Now, the first thing that you have to do in order to apply additivity to any kind of property is you have to have a quantitative assessment of that property. Just like for molecular weight, we have the atomic weights. That's a quantitative assessment of the weight of the atom. We also have to be able to quantitatively assess aromaticity. And this is something that is an entire field of research, which of course I don't have time to go into today. I'll just say that very broadly, there are four main criteria for evaluating aromaticity. And they're based on what we call the energetic, the geometric, the magnetic, and the electronic criteria, which are each of them is an entire field unto itself, very, very interesting, that are sometimes also very controversial. What I'm going to talk about today is just the magnetic type of evaluation, because that's the one that we use the most in my group. And I'll explain to you where this comes from. The idea of the magnetic criterion of aromaticity goes back to what's called the ring current model. What the ring current model states is that benzene is very much like a wire loop that you put into that you can put into an external magnetic field. If you think about what characterizes benzene, it's these 6p orbitals on the 6 conjugated carbons in the ring. Each of them has an electron. And if you now put this molecule into an external magnetic field that is perpendicular to the molecular plane, these electrons are going to start moving around in what we call cyclic delocalization. As a result of this cyclic delocalization, an induced magnetic field is formed. Now we know this because if you ever consider the experimentally measured chemical shift of protons on benzene, you know that they have a they are very downfield shifted to about 7.2 ppm, which is an indication of the magnetic environment that they are feeling, which is due to this induced magnetic field. Now, for us as computational chemists, we don't really like to use protons as our evaluator for aromaticity because they can also be influenced by other things within the molecule. And so what we do is we take something that we call a ghost atom or a dummy atom, which is actually not a real atom. And so we can place it anywhere we want. It doesn't have to be bonded in any kind of chemically meaningful way. What we do is we place it above the center of the ring, as you can see here. And we ask what is the chemical shift that dummy atom is feeling at that location. Now, because this is not a real atom and it doesn't actually have a nucleus, this method is called nucleus-independent chemical shift. Basically, what it's asking is, what is the chemical shift at this point in space? And usually, if the value comes out to be positive, we'll say that there is a paratropic current, which means that the molecule is most likely anti-aromatic. And if the value is negative, that indicates there's a diatropic current, which we generally understand as the molecule being aromatic. Now, NICS is, again, a method that's been around for about 20 years or more, and it's undergone many different developments and different types of modifications and refinements, but we won't go into that. What you need to keep in mind is just that negative values for us generally mean that the molecule is aromatic. So we now have a way to evaluate aromaticity in monocyclic systems, but what happens if you go to polycyclic systems? In this case, what's often done is that you might take the NICS value at each of these different rings, which gives you a feeling for what's happening in each system. And this is also why people sometimes talk about local aromaticity within larger molecules. Another thing that you can do is you can get a more refined description of what's happening in the molecule if you take an entire series of these probe atoms and you place it along a line that goes through the backbone of the molecule at a certain height above it, just like we do regular NICS. We don't do it at the molecular plane, we do it above. And this can give you what we call a NICS XY scan, which really shows you how the magnetic field is changing as you go through different parts of the molecule. So we do have a method to evaluate the aromaticity of molecules in a quantitative way. Now we have to answer the other question, which is when we're talking about additivity, what we're saying is that the whole is the sum of its parts, right? So how do we then break down these molecules into different parts? What would be the parts that we would consider in trying to find additive behavior here? One option is to just break them up into their monocyclic components, so that would be individual benzenes, but they're also made up of different bicyclic components or tricyclic components. How do you know what the right components are to use in order to find additive behavior? So what we did is we actually thought all of these should be important. And so what we did is we started out with the monocyclic component, which is benzene, and we did a Nix XY scan, as you can see here by this arrow, for benzene. And what we get is this green curve here. And as you can see, all of the values are negative. That indicates the diatropicity of benzene, or what we call the aromaticity of benzene. And then we looked at naphthalene. And we said, well, if naphthalene is just two benzenes in a row, what we should get is this kind of W shape, right? These two green curves. But in fact, if you do the Nix XY scan of naphthalene, what you get is this black curve. And the difference between them is what we see here as the pink curve. And we call that pink curve the bicyclic correction. It's basically what you need to add on top of benzenes if you want to be able to describe the behavior of naphthalene correctly. We then moved on to our two tricyclic components. We have anthracene, which is the linear one, and phenanthrene, which is the angular one. And for each of them, we also found that you have to have corrections. And you can see here that in anthracene, the correction is negative. In the middle, that shows the stronger diatropicity of the middle ring. In phenanthrene, it's positive because the middle ring is actually less diatropic. So this is now our library of building blocks. And the question is, can we use this library in order to predict the behavior of larger systems? If we can, then that is in fact the corroboration of this idea that the behavior is additive. And I'll show you an example of how this works. We take this pentacyclic system and we break it down into these different types of components. You can see, so this molecule has 5 benzenes in a row. So we just place these 5 curves in a row, just like they appear in the molecule. Then we place our 4 naphthalenes, and just like the naphthalenes are overlapping in the structure, we also place them overlapping here in the plots. And then we have our 3 tricyclic contributions. 2 of them are angular, 1 of them is linear. You can see them here as well. And what we do is we sum up the contribution at each distance point. And that's the graph that we get. Essentially, what this means is that if the correct behavior, if the magnetic behavior of this molecule is really encoded within these smaller components, then our predicted line should be very close to what we get if we did an actual DFT calculation of the Nix XY scan. And this is the actual calculation, this black line. You can see that the fitting is actually quite remarkable. The difference between them is just this gray line up here, which is very close to 0 throughout the scan, as you can see. What this tells us is that, in fact, we can describe the magnetic response of larger systems simply based on their smaller components, in this case up to tricyclic components, which kind of substantiates our hypothesis about additivity. What you can see in this line up here, the fact that it's not 0 throughout the entire scan is not because of errors in the calculation. It's actually because we omitted certain contributions by design. If you look at this structure, there's also 2 tetracyclic circuits and 1 pentacyclic circuit that are possible to sustain within the structure. And we deliberately neglected them, and we still got a very good behavior. That indicates that those contributions are negligible or very, very small. And that's why we can get the correct behavior even just using the first components, the monocyclic, bicyclic, and tricyclic. Okay, so just to show you that this is not just happening in polybenzenoid systems, but is in fact a more general phenomenon in polycyclic systems, we also incorporated different types of heterocycles. You can see here both aromatic and anti-aromatic systems. You can see single substitutions, but also molecules that have more than 1 heterocycle in them. And in all of these cases, we get a very good fitting between the predicted and the actually calculated scan. We can also see that when we mix and match different types of heterocycles. So it shows you that the behavior really is general. In fact, it's so general that we could code it up and we could create this very useful code where all you have to do is put in your structure and it will calculate for you what the predicted scan is based on the library of building blocks that we've already hard-coded into it. So the conclusion from this so far is that the magnetic response of these PASs is in fact additive. But there's an underlying conclusion from this that I think is even more important, which tells us that actually the delocalization in polycyclic aromatic systems is localized. What do I mean by that? What I mean is that The fact that we only needed up to tricyclic systems in order to describe larger molecules indicates that the delocalization that I talked about before, the cyclic delocalization, doesn't spread out over the entire molecule. It's in fact limited in its scope to the smaller components that we used in order to describe the system. Otherwise, adding another ring at the end of the molecule would change the entire behavior of the system. The fact that it doesn't do that is the indication that the behavior is localized. So we asked ourselves, how local is local? What are the smallest components we need? So far, our NICS work had showed us that what we need are tricyclic systems, but we wanted to corroborate that with a different kind of method, something else that might tell us that this is the right conclusion to reach. So we turned to something that we've been using more and more in our group in recent years, which is deep learning. And what we did here was we trained a model on data that we had generated in our group. Our group has made several different databases. We call this the COMPASS project, so the computational database of polycyclic aromatic systems. We have almost 2 million molecules already in this database. And among those molecules, we have all of these different polybenzenoids. So we extracted all of the systems that have up to 6 rings, plus a selection of ones that have 7 rings. And we placed them into this grid of points. Each of these pink points is one of those NICS points that I told you about before, which is measuring the chemical shift at that location. So essentially what we're doing here is we are sampling the induced magnetic field around the molecule, not just at one point, but in a 3D space around each of these molecules. And then we can take that data and we can train a model so that it can predict the induced magnetic field around a molecule that it hasn't seen before. And the idea is that if it can predict for larger systems, then that means that in fact the additivity is correct. So what we did is we trained it on those molecules, which were all the way up to 7 rings. And then we asked the model to predict the behavior for molecules it hadn't seen before. And you can see that for molecules that contain 7 rings, it does pretty well. This is the mean absolute error. This is in ppm, that's basically how far off is it for the different NICS values. You can see it's only a fraction of a ppm. But as we get to larger and larger systems, the error grows, which in itself would suggest that this behavior is not additive, because if the error grows as the molecule grows, that seems to indicate that the behavior changed as you add more and more rings. But we were a little bit suspicious of this outcome because our NICS work from before had indicated that that's not the case. And so these 2 very talented undergraduate students, Yair and Aviad, who were working on this, came up with an idea. And they said, maybe this is not the chemical behavior. Maybe this is an inherent problem with the graph neural net, that it struggles to generalize to larger systems. So essentially, the model knows that it was trained on molecules up to 7. And so when it goes up to larger systems, it's confusing for the model. So how can we solve this problem? Well, what we did is we said for each of the points that we're trying to predict, let's find the ring that is closest to it. And we associate it with that ring. And then instead of giving the model the entire structure of the molecule that it needs to predict, we only give it a certain surroundings of the ring to which that BQ is associated, or that ghost atom is associated. So in this case, what we do is we call this a 2-hop. So if this is the ring to which that ghost atom or that probe is associated, what we will give the model is that point and this environment around that point. So in essence, what the model is obtaining as the input is not the entire molecular system, but just this cutout of the system. And you can see that for the same molecule, depending on which ring is closest to the point we're trying to predict, it might see a different part of the molecule. And when we do that, this is what happens to the errors. You can see that they decrease substantially. And in fact, there's no difference whether we're trying to predict a 15-ring system or a 10-ring system, which is again very strong evidence for this additivity. The fact that the model can predict the behavior of a 15-ring system without even seeing the entire structure is already a strong indication that the behavior of at a certain point doesn't depend on the entire structure, which is again corroboration of additivity. So just to show you what that looks like, this is, for example, a molecule that we studied. You can see we're looking at different heights of the different cross sections from the molecular plane. The field, these are the contour plots of the induced magnetic field. This is the ground truth. So the DFT calculated values. These red lines are the predicted values, and you can see that they overlap very nicely. And this is if we color in the strength of the magnetic field. You can see that within the plane, it's of course the strongest. And as we move farther and farther away, the field decays, which is exactly as it should. If we look at the errors that we find, you see that the errors are strongest are largest within the plane, which makes a lot of sense because this is also where the values are the largest. But again, as we go up, the errors get smaller and smaller. And in all cases, the errors are a fraction of the predicted value. So the prediction is very accurate. But we still have our last question that we haven't answered yet, which is, so how local is local? Because remember, the results that I showed you, we got them when we trained the model on molecules up to 7 rings. We call that the model 7. We wanted to know how small can we go and still get a good prediction. So what we did is we successively made the data that we were training on smaller and smaller. If this is the model 7, we then took a model 6, which was only trained on molecules that have up to 6 rings. And you can see that the prediction is still pretty good. It gets a little bit worse because we're now also training on less data because there are fewer molecules that have up to 6 rings. We go to the model 5 and the trend is similar. We go to the 4 and it's still pretty good. But then we have to remember that when we train on the model 4, what this means is that the model has only seen 9 molecules and it's predicting for molecules that are almost 4 times larger than it, which is really a very impressive success rate here, considering that this is about 1.5 ppm. DFT error in NMR is about 1 ppm as well. So this is not bad at all. But then we went to the model 3. And we got this result, which was very disappointing because it seems to show a huge jump in error, which would suggest that you cannot really omit the 4-ring systems and still get a good prediction, which goes against what we had seen before, because before we were saying that we only need the tricyclic components. But when we thought about it, what we realized is that when we do the model 3, we're actually not training anymore on any of these systems. Now, most of them don't really matter, but one of them is very important, and it's this triphenylene unit, because it introduces the branching motif, which doesn't exist in this library. So we thought, what happens if we now go back to this model 3 and we ask it to predict for molecules that don't have a branching motif? And you see that when it has to do that, it does much better. So really the problem is not in the size of the system that we're asking it to predict, but the fact that it cannot predict for a kind of motif that it never saw before. And here you can see the error for the molecules that contain that branching motif. You can see that's what's driving up the error. And if you put this back in the context of all of the other models, you can see that going to the model 3 is a smooth continuation of what we had been seeing before. And the slight increase in error is simply because of the smaller data set that we were training on. So overall, I think that what this data shows is that the idea of locality that we saw from the very beginning with NICs is supported, that indeed the tricyclic units are the minimal units that we need in order to get a good prediction for much, much larger systems. But if we do want to include branching, we have to include tetracycles. And again, not all tetracycles, but specifically the branching motif. So overall, what I would like to say as my take-home message for today's talk is that the delocalization in polycyclic aromatic systems does appear to be meaningful, only up to tricyclic subunits. The reason that I think this is interesting is because in organic chemistry, one of the things we learn is that conjugated systems are conjugated throughout, meaning that as long as the system, as we continue adding more and more conjugated units, that means the behavior becomes more and more delocalized. And what this work shows us is that that is not true in a trivial way. There is an extent of delocalization, but we shouldn't assume that the entire structure is delocalized just because we can draw double bonds or conjugated cyclic systems throughout the system. As I said from the very beginning, additivity is a very powerful tool. We use it every day in chemistry. And so if we can also apply it to complex concepts like aromaticity, it can have a very important practical and conceptual impact. Practically, because this now allows us to predict the behavior of much larger systems at a fraction of the cost. Conceptually, because it tells us that the behavior that we thought we knew for these molecules, that they're fully delocalized, is in fact not true. And this can affect how they behave in all sorts of different circumstances. It can affect their properties, etc. And then finally, what I will say is that when we are applying these kinds of deep learning or machine learning models, it's very important to always have domain knowledge and not just apply them blindly. The fact that we knew going in and we had an expectation about the behavior of these systems is really what allowed us to use these models meaningfully. Otherwise, we would have been stuck at the point where the errors exploded, and we wouldn't have been able to actually reach the conclusion of locality based on these models. So I'll just wrap up by thanking my group for all of their work on this project. What I talked about today started out with Patrick doing the heterocyclic additivity for the Nix scans, and then the deep learning work today was led by my postdoc, Dr. Chakraborty, and these two great undergraduate students, Yair and Aviad, who did this as a project for their final year in undergrad. And I'm very grateful to them and to Professor Alex Bronstein, who is our collaborator from the computer science department, who worked with us on that. And I'm thankful, of course, also to the funding agencies that support our work and allow us to do what we really like doing, which is playing with polycyclic aromatic systems. And thank you all for your attention.
Thank you so much, Professor Ghoshani-Paran. That was a brilliant talk. I thoroughly
Thank
enjoyed
you.
it. It was brilliant. We have got time for a quick question. Just to all the viewers today, you can continue to send questions into the Q&A for Professor Ghoshani-Paran to answer offline, and we'll follow up with an email afterwards. But we have got a question that I'll share now as we have got time. So it's from Rengis, who says, "Thanks for the nice talk. So this question is about the Nix XY scan.
Yeah, let me see real quick.
At what distance is the dummy atom, or what distance are the dummy atoms kept above the plane? And why is that distance chosen?" And then there is a
That's
quick
it.
follow-up question, sorry, and
Yes.
have you tried the scan in the Z-axis?
Yes, of course. Okay, so let me answer that. First of all, that's a great question. The way we do this is that if this is the molecular plane, we place the Nix probe above. Now, there's different ways of doing this. You can usually, by convention, we either do it at a height of 1 angstrom or at a height of 1.7 angstrom. Now, the reason that we choose them is different. So part of our problem when we calculate Nix is that there are also what we call sigma contaminations, meaning there are effects that are coming from the sigma electrons, which can cloud or obscure what we're trying to see from the pi system, which is where the aromaticity is happening. So if we can separate sigma and pi effects, for example, if the molecule is planar, we can actually identify which orbitals are pi, which are sigma, and then take only the pi orbitals. Then doing it at a height of 1 is perfect. If we cannot separate them, for example, if a molecule is slightly not planar and sigma and pi mix together, then it is usually safer to do it at a height of 1.7 because we have shown before, and this reference down here on the screen, that at the height of 1.7, we get the same qualitative agreement, so we can see the same aromatic behavior, even though we cannot separate quantitatively the sigma and pi. I hope that answers the first question. The second question is about the Z-scan. That's something that was actually published many years before. I think that came out in 2006, if I'm not mistaken. That's the original Nix scan. You basically take a line and you go up from the molecule. What that shows you is the decay of the field as you move away from the system, and that allows you to see, for example, how quickly the diatropic or paratropic fields decay, and that is a good way for really ascertaining whether what you're seeing is aromatic behavior or maybe just spurious local negative or positive values.
Wonderful. Thank you so much. Just in the interest of time, we'll move on. But as I said, you can keep sending questions in, and we'll send those over to be answered. So
Thank you very much.
thank you once again. Fantastic. Okay, so we will very soon move over to our next speaker, but just before we do that, I would like to highlight the RSC's multidisciplinary journals. Our flagship general chemistry journal, ChemSci, is Diamond Open Access and therefore always free to publish in. ChemSocRev publishes review articles covering important and impactful topics at the forefront of the chemical sciences. We also have ChemCom, which publishes urgent communications of outstanding significance across the chemical sciences, and RSC Advances, which is our community-led open access general chemistry journal. So again, you can learn more about the RSC's journal portfolio by using the QR code shown on screen and the short link as well. So, with that, it is my pleasure to introduce the next speaker, who is Professor Dean Tantillo. He is Distinguished Professor of Chemistry at the University of California at Davis. He and his lab apply the tools of theoretical chemistry to problems in mechanistic bioorganic chemistry, chemical biology, and mechanisms of organic and organometallic reactions of synthetic relevance, all while advocating for the accessibility of chemistry for visually impaired students. He recently published this cover article in ChemSci on barbaryl cation formation and rearrangements, and is a member of the advisory board for organic and biomolecular chemistry. Today, he'll be telling us about cyclic electron flow, ring current, aromaticity, and pericyclicity, the same or not the same. And I'll hand over to you now, Professor Tantillo.
Okay, great. Let me share my slides. And okay, well, it's great to be here. I'll say the most important thing in that introduction was that cake because I baked it. I also want to thank RC for doing this and for inviting me. Probably not surprised to learn I'm a big fan of RC. So I've been involved with journals here for a long time. So what I'd like to talk about today are a class of reactions that are most associated with aromaticity, and those are pericyclic reactions. So let's jump right in and we'll talk about these different concepts and how they're related and how they're not the same, and how they are the same, and how much you should use them as synonyms and not. Okay, so if we're going to talk about pericyclic reactions, we need to talk about Woodward and Hoffman's classic conservation of orbital symmetry. That's the treatise on predicting whether or not an apparently pericyclic reaction should occur. And Woodward and Hoffman came up with a set of rules that tell you whether or not a reaction was allowed or forbidden. And this is based on looking at certain orbitals that are involved in bonding changes during these reactions and deciding then, is the symmetry conserved as you do the reaction and therefore the reaction is allowed, or is the reaction forbidden if the symmetry is not conserved? And if you read the conservation of orbital symmetry, which I show here in book form, but it's also a long article, which is exactly the same as the book, you get to a certain chapter called violations, and that says there are none. So there are no violations to these rules, and nor can violations be expected of so fundamental a principle of maximum bonding. Okay, and this is a pretty bold statement. And I was a postdoc with Roald Hoffman, and he tells me that this actually was Woodward's statement. And I want to talk a little bit about violating the rules. And as I said, I worked with Roald, so I'm not allowed to violate the rules, but I'll give you some thoughts on what it actually means to violate the rules and how that's connected potentially to aromaticity. Okay, I did want to point out that, this is not just a historical issue. This is an issue that is current today. So here's a paper from ChemSci, just from this year, by another one of my physical organic heroes, Barry Carpenter, who argues that the terms allowed and forbidden are probably too severe. And in this paper, he shows reactions where the differences between allowed and forbidden reactions can actually be quite small. Now, why did I say this is related to aromaticity? Well, there's actually a long history of this. So long before the Woodward-Hoffman rules, there was this amazing paper in 1939. This is an RSC journal, actually, where it was pointed out by Evans that the transition state for a Diels-Alder reaction is very much like benzene. Um, this was kind of the extent of the theory at the time, but that alone was a pretty uh, um, ahead of its time observation. And then in the 60s, around the same time as the Woodward-Hoffman rules and just after they were published, Zimmerman pointed out more directly the connection to aromaticity and how if you look at the orbitals of the pi systems that are involved in pericyclic reactions, you can treat them uh, just like aromatic minima, and you can look for Huckel and Mobius orbital patterns as well. So there is definitely a connection between the orbital arrays in the transition states for pericyclic reactions and the types of aromatic systems that Renata was talking about, for example. So the argument for pericyclic reactions was that if you had an aromatic array of orbitals with the right number of electrons in it, then your reaction would be allowed. And if you had an anti-aromatic system, then it would be forbidden. So where do we come in? Well, we come in by basically just following Paul Schleyer, who was another one of my heroes in physical organic chemistry, who came up with the Nix concept that Renata mentioned. And what he did a long time ago was show that you could characterize pericyclic reactions by looking at their Nix values along reaction coordinates. So that's what's shown here for just one example. So this is a 2 + 2 + 2 cycloaddition of 3 acetylenes. So there's acetylene. This is the transition state for 3 acetylenes combining to make benzene. And shown in the plot here on the left is the reaction coordinate for this reaction. And what you have here are that there's no energetics here. These are all Nix values. So in the dots, you have the total Nix value, and you see that it gets the most negative near the transition state. So that's consistent with aromaticity, as Renata told you. And then you can break that into pi and sigma components, and you can see that the pi component, which is the squares, gets consistently lower, and that makes sense because you're building up the benzene pi system. And then the sigma component, the in-plane component here, that's where you're delocalizing electrons as you combine the acetylenes. That is most delocalized near the transition state, and then it loses delocalization as you make the benzene framework based on Nix. Okay, so you can follow Nix along a reaction coordinate to look at a pericyclic reaction. So what we wanted to do is try to apply this more broadly to look at allowed and forbidden reactions, and basically make a handy tool for people to use, just to make the debate about whether certain reactions were really violations of the Woodward-Hoffmann rules maybe clearer, or maybe just give people more things to argue about. So, and that kind of boils down to the fundamental question of what really makes a reaction pericyclic. So let's jump into that. So this is work by my grad student Will, shown here, clearly demonstrating some sort of pericyclic reaction. And he developed this tool, which he calls peri-reaction. This is available on GitHub. I don't have the link here, but if you go to this paper, you can find it. And what this tool does is generate plots like this. So let me talk you through this. So here are two classic pericyclic reactions, a 6-electron electrocyclic ring closure and a Diels-Alder reaction. So in this plot, you have 3 curves. So if you look first at the blue curve, that's just the reaction coordinate, the IRC, the intrinsic reaction coordinate, and that's just energy. In blue, the energy goes up to the transition state and comes back down along the reaction coordinate. Okay. Then in red, you have the Nix value. So this is actually the average of a Nix scan in both directions, above and below the plane, because we're going to look at some systems that aren't symmetrical. But all you need to really remember is more negative is more aromatic and positive is anti-aromatic. And as you see, as you go along the reaction coordinate, it goes down, and it's most negative or most aromatic here at the transition state or near the transition state. And then it goes back up. And then in green is what's called the multi-center bond index. And this is basically like a bond order that you've heard of before, except it's spread over multiple bonds. So in this case, it's the bond order, the multi-center bond index for 6 bonds, because there were 6 bonds involved in this reaction. And all you need to really know about that one is that there is more delocalization when that goes up. So we have 2 measures of delocalization, one electronic, that's the multi-center bond order, and one that's magnetic, that's the Nix. So if you have more cyclic delocalization, the Nix value should go down. If you have more delocalization, it's not specifically cyclic delocalization, but cyclic delocalization counts, the multi-center bond order should go up. Okay, and so that's exactly what you'd expect for a pericyclic reaction. As you get near the transition state structure, there's cyclic delocalization, so the Nix goes way down and the delocalization goes up. And then this is the Diels-Alder reaction again. So here, this is just shown in the reverse direction is what you normally expect. So the energy goes up at the transition state, the Nix goes down, and the multi-center bond index goes up. Okay. And then shown in these plots below, what you have is actually the Nix scan, okay, in distances away from the plane along the reaction coordinate. So right in the center is the transition structure, okay, and then on the far left and far right are basically the reactants in the product, and the Nix is color coded. So the darker blue is more negative, and the darker red is more positive. Okay, and so this is really what you'd expect. This is kind of this is, again, remember, this is not one structure. This is a collection of structures along the reaction coordinate. So for a reaction with an aromatic transition state, you'd expect to see this sort of picture where there's a lot of dark blue near the transition state. Okay, and that's what you see for both of these reactions. Here are a few more classic pericyclic reactions. 4-electron electrocyclic ring opening with the correct Woodward-Hoffman allowed stereochemistry. So there's blue in the middle. You see the Nix go down. Now you see the multi-center bond index go down. That's not a bad thing. As you switch between 4n and 4n plus 2 electrons, the sign of that actually changes. So that one should go down for the 4 system. And then as you go back to 6, the Nix will always go down, and then the multi-center bond index will either go up or down. Okay, so all of these have blue in the middle in these plots, and the Nix value sharply goes down near the transition state. So it looks like this not surprisingly, is a useful way to visualize a reaction coordinate for a reaction that is pericyclic. And here, saying it's pericyclic if it has cyclic delocalization somewhere along the reaction coordinate. Okay, so when would you use this? Well, you might use this for some reactions where people debate about whether or not they're pericyclic. So these are 3 reactions that on paper look pericyclic, for which you could draw pericyclic arrows if you wanted, but these are actually reactions that are pseudo-pericyclic. So pseudo-pericyclic means looks like pericyclic, but not, because at some point in the array of rearranging electrons, there are orthogonal orbitals involved. So for example, in this one, you could draw this as a 6-electron electrocyclization, but what's really happening is you're using both this pi system of this carbonyl and a lone pair on this oxygen. Okay, and so because there are orthogonal orbitals there, you don't have continuous cyclic orbital overlap, and so you don't see the cyclic delocalization in the Nix, for example. All right, same thing here. This is the cycle addition version, and this is a sigmatropic shift version. So in these cases, you don't see much of anything. You see maybe a little bit of red in the middle, but not much of anything. Okay, and you can see that in the plot, the Nix lines are very flat, and the multi-center bond indices vary a bit because in these cases, you're getting other sorts of delocalization. So this is a quick way to decide whether or not a reaction is pericyclic or pseudo-pericyclic if that option is available to you. Okay. Here's what it looks like if you have a reaction that's clearly just not pericyclic. This is one that we looked at before. Why do we even look at this one? Because you could formulate this one if you thought of this reaction as a homoallylic cation with an interaction here. You could formulate this as a cycloaddition, but this is not. It's still a concerted reaction. There's only one barrier, but there's no point along the reaction coordinate with a significant sharp drop in Nix value. There are these drops in multi-center bond order, which is interesting, and that's telling you something interesting about this reaction, because there are different stages to this concerted reaction. It's quite an asynchronous process where you're making different bonds and picking up different delocalization. So this tool is also useful for looking at concerted reactions that are not pericyclic. So in one picture, you see that it's not pericyclic, but you can track the different bond making events that are occurring. And here's a plot where there's quite clearly nothing much going on. Okay. What are the limitations? Well, this is obviously useless. You just have a plot full of blue. Okay, we looked at this one because this is a classic example of what's supposedly a forbidden reaction. In this case, if you look at it in this reverse direction, the ring opening direction, this would be a 4-electron electrocyclic ring opening that opens this when it should be con rotatory. And so we wanted to see if it showed any signs of anti-aromaticity. There's been subsequent work that suggests it actually opens con and then relaxes the disc, but this tool is really useless because there's such a concentration of electron density in the ring and also from the bridges here that everything is just distorted by that. So uh, the magnetic criteria doesn't work very well because you have all these other electrons around, and the multi-center bond index is complicated because you have these cyano groups involved in delocalization. So this is a case where this tool is not very useful. So I always want to point out the limitations of things. Okay, so where is it useful? So we've used it in a couple places ourselves, actually before we published the paper on the tool. So this was a collaboration we had with Dan Whitehead, where he was developing reactions like this one here. So what he does is he protonates this imine, and there's a cyclization, and he was curious as to whether or not this was really like a Nazarov cyclization that was a concerted 4-electron electrocyclic reaction that had pericyclic character. So you can calculate the transition structure for that. And then you can throw our peri-reaction tool at it. And what you see is, well, there's a dip in the NICs near the transition structure. But you'll notice that this dip is less than 1 ppm in the average NICs value, which is quite a bit less if you look back at the scale of some of these other ones. They were, for example, go to a good one. These are dropping like 10 or 20 ppm. So this is quite a bit less delocalization. And the multi-center bond index here isn't very useful because, again, you're building an aromatic, highly delocalized system as you go. So it's hard to tell what delocalization is coming from the transition state delocalization versus the new pi system you're building in. Okay, so based on this number being small, and based on the bond lengths involved here, so for example, this CC bond is quite long, we ultimately concluded that this is probably not considered, truly pericyclic. Although you can even sense the hesitation in my words because that is actually a complicated question. So here's the comparison from before. So here's an electrocyclic ring closure that you would definitely say is pericyclic, and this drops about 20 in the NICs. Okay, so that was our conclusion. It looks more like the nucleophilic addition of an imine lone pair into, again, this would be protonated into an alpha beta unsaturated iminium ion. Okay, we decided to use this for some transition metal reactions. So we looked at this reaction here that has a potential transition structure that looks like it could be pericyclic. So we were curious about that. This transition structure was annoying to get, as you could probably tell by the fact that the picture looks so complicated. We just cut out the center of it, and this looks very delocalized here. For this is a hydrogen transfer between 2 palladiums, and there's an allyl subunit in it. So what if you throw peri reaction at this? Well, you get this plot here. You do see the multi-center bond index go up near the transition state, and you see the NICs drop down. Again, it's not a very big drop. It's about -5. So we don't really know what, if that's meaningful in a case like this. So what we did is we compared it to something that people considered to be aromatic, this metallobenzene with a palladium in it. And this one actually has a NICs, an equivalent NICs value of -2.5. So all we can really say here is if you consider this to be aromatic, you should consider this transition state to be aromatic and therefore probably pericyclic. But if you don't consider this to be aromatic, then don't consider this one to be aromatic. I have a pretty easygoing attitude about such things. Okay, so what about reactions that are supposed to be forbidden, supposed to have broken the Woodward-Hoffman rules? Well, we looked at a bunch of those. Here's one. This is a reaction from a total synthesis, excuse me, by Brian Stoltz. So here there's a 4-electron electrocyclic ring opening that opens dis when it should be con. So in this case, you actually get a plot that looks like it's pericyclic. Well, how could that be? Well, if you actually look along the reaction coordinate, what you see in the transition structure is it's actually not opening in the forbidden geometry. It's actually what you might call monorotatory. The two ends, one end just pulls apart as the other one rotates, and you get quite a twisted pi system there. So the molecule is actually trying really hard to avoid the anti-aromatic geometry and actually picking up some goodness in doing so. So I would say that's not a violation because it doesn't get into the forbidden geometry. And then later on it relaxes into the product that has that geometry. Okay. So here's another case. So this is a case that was published by my PhD advisor, Ken Hauk. So I'm not supposed to disagree with him either. So let's look at this one. So he says that this is a violation. So is it? So this is a case where you have, this is a large system that has a 7-membered ring on one side, a 5-membered ring on the other. So there are 2 double bonds here. There's an exocyclic double bond here to this ring. Same thing over here on the 7-membered ring. And this can close dis or con. So here's the con pathway. So sorry, here is the reactant. Here's the con transition state and the dis transition state. If you follow the Woodward-Hoffmann rules, dis should be favored. It should be the allowed pathway. Con should be forbidden, but the barrier is lower for con than for dis. So this looks like a violation, okay? And the argument in this paper is you're getting around that orbital symmetry restriction because this is a very highly polarized transition state structure, which makes some sense. So what does Perry reaction say about this? Well, there you go. So blue is the reaction coordinate. Now, in this case, you actually see an increase in delocalization in the bond order, but you see a spike in the Nix, which it looks to be consistent with anti-aromaticity. And you see your plot is now red instead of blue. So this kind of surprised me. I didn't think this would happen because I was convinced that there are no violations. So I begrudgingly have to say that this is, I don't know if I would say it's really a violation, but this is a transition state for a concerted reaction that looks to be cyclically delocalized, but has an aromatic transition state that is lower in energy than, that has an anti-aromatic transition state that's lower in energy than the aromatic transition state. Okay. And this is not just because these two things on the side are contributing their own aromaticity. If you look at systems that don't have those rings, you get the same sort of behavior. You have a bump in the Nix, okay? And this, I think, is because it's highly polarized, which is providing a counterbalance to the badness of the anti-aromaticity. And this is actually not something that Woodward and Hoffmann said couldn't happen. So I showed you the there are none part of this chapter, but it goes on to say that there are possibilities for not following the rules. You could have a stepwise possibility, so something that's not concerted. There are discrete intermediates. When they even said that you could, this was quite figurative language, you could have a Maxwell demon grabbing a molecule of ethylene and using his strength to force it together in a forbidden geometry. But without such demonic intervention, molecules will rarely comport themselves in such a fashion, okay? But nonetheless, the possibility remains that molecules might be constructed where the symmetry forbidden path would necessarily be followed. So this possibility was allowed, pun intended, by Woodward and Hoffmann, okay? So what does Hoffmann say? So there is this really interesting paper by Rold and Hauk and my friend Jeff Zeman just a year ago on this issue, and this is what they say. They say that, well, maybe we should just say that there's more than one type of violation. There's a violation where if you count up the number of electrons, and you get the wrong product, that's a violation. But then there's a violation where you actually violate the rules. But that's not very specific. But they do say that to be allowed, what you need is to maintain a degree of bonding in all the filled orbitals if you're going to be allowed. And that's what I agree with. And that was really the point of our tool. So we were kind of looking at reactions where things looked like violations, but the reactions were occurring, the bond making and bond breaking was occurring asynchronously. And it looked to us like at no point along the reaction coordinate was there continuous strong cyclic overlap of the orbitals. And so we didn't feel like the rule should apply, but people kept asking, well, you know, how do you know if there's strong cyclic overlap? So that's why we did this project. So that kind of brings us back to the question in my title. You know, are these things the same, or how should you think about them? Well, I think for a pericyclic reaction, the cyclic electron flow, super important. If you have cyclic electron flow, that should generate a ring current. It's not the same thing, but it's a consequence of it. Aromaticity is a very useful concept that's still not rigidly defined. Rold has a really great article about reductionism where he talks about aromaticity and how useful it is, but how you can't really reduce it to physics. And I recommend that you go track that down. But generally, the assumption is if you have a ring current, you can say something is aromatic. And I would say for a reaction to be really pericyclic, you need to have cyclic electron flow, and therefore you should have a ring current. So all these things are related. You know, your opinions may differ, and I'm fine with that. But if you want to know how delocalized your transition state is, or if there is good cyclic delocalization along your reaction coordinate, feel free to use the pericyclic reaction tool that my student will develop. And with that, I'll just thank Will and the rest of my group and the National Science Foundation for support. And I'll thank all of you, and I'm happy to answer any questions if there are any. Thanks a lot.
Thank you so much, Professor Tantillo. That was another fantastic presentation. I thoroughly enjoyed the presentations that we've had in this session. I think just in the interest of time, I'm going to ask you to send questions into the Q&A to answer offline, if that's okay. Yes, thank you. Thank you again, both of our speakers today for joining us. We really appreciate it, and they've been fantastic talks this afternoon. So thank you so much. So as I've mentioned, do continue to send your questions in. We'll send those over to our speakers, and we'll get some answers for you. So that brings us to the end of our webinar today. Thank you so much to everyone who's joined us. And as I've mentioned, to our speakers as well, Professor Renana Ghoshoni-Paran and Professor Dean Tantillo. You can follow up with us as well at the email addresses listed. And as I've mentioned, we'll send an email out after this event with some follow-up responses to questions that we didn't get to today. We hope to see you all at a future desktop seminar. You can find out more about that using the QR code currently on screen. So just before you go, if you are interested in some more historical discussions for the bicentennial of benzene, our news magazine Chemistry World has published a number of fascinating articles already this year about benzene and its discoverer Michael Faraday. We invite you to read some of them by scanning the respective QR codes. And just to finish off, I will end on a call to action. If you are interested in helping us improve publishing and our services, please sign up to join the RSC Digital Research Lab, and you can do so using the QR code that's currently on screen. So thank you again to everyone that's joined us. Thank you again to our speakers, and bye for now. We hope to see you at another desktop seminar very soon.